everybody. This is your Geometry Chapter 4 study guide, and we're going to start on this page right here. Now, if you hear that sound where it sounds like a jet's taking off, that's the computer. And sometimes it does that. It's doing it right now. Anyway, I'll try to speak as clearly as I can. Basically, these are just short little tiny proofs. So for example, if we know that M bisects segment AB, because that's the given, then how do we know that AM is congruent to MB? Well, because it's a bisector. When M bisects a full segment, that means the two sides would have to be congruent. So this is the definition of a segment bisector. In the next example, they have two lines that are parallel. They tell you that line G is parallel to line F. Remember that that's how it's marked with two little arrows? So, if line F and G are parallel, then how do we know that angle 1 is congruent to angle 4? Well, those are called corresponding angles. They're in the same position of the intersection here and the intersection here. They're basically on the top right portion. So, those are called corresponding angles. And we know that they're congruent because when two lines are parallel, the corresponding angles are congruent. So we say that the reason is that the corresponding angles congruence theorem. Now I've given the sub-directions when I make these videos that they could pause at any time if you're having trouble writing everything down. So for example, right now they could pause to make sure that everybody's written everything down. Or same thing for this one. They could pause right here and make sure that that's written down. The next one is if line F intersects line W, these weren't labeled, but prove that angles 6 and 7 are congruent. Well, what would be the reason? Well, those two are called vertical angles. When two lines intersect one another, the vertical angles are congruent. So the theorem that we would state here would be the vertical angles congruence theorem. So again, if the sub wanted to pause the video at this moment to make sure everybody is writing everything that they need down, they could do that. Then we have these examples. If you have segment A being the same as segment B, or sorry, AM being the same as segment MB, that's what I meant to say. This statement means that the measure from A to M is the same as the measure from M to B. Now, the second statement says that therefore the line segments themselves are congruent. And this would be the definition of congruent segments. Because their measures are the same, therefore they have to be congruent. And there's that example. If if you have two pairs of parallel lines, it looks like that's what we have, but it's really not. These two we know for sure are parallel, but we're not quite sure about those two. So, what do? Well, we go from what they give us. And we can say, okay, G and F are parallel, and angle 3 is congruent to angle 2. So I can mark those. Here's angle 2 and here's angle 3. I think that's angle 3. Nope, it must be this one. Well, I can't quite tell which one is angle 2. Again, it seems like it's this one. Yeah. Well, what will we do here? Well, we could say that if we wanted to prove that those two lines are parallel, if we could prove that angle 3 and angle 4 are the same angle, then those would be alternate exterior angles, and when those two are congruent, then the two lines E and H would have to be parallel. So I think that's where I'm going to go with this. I'm going to say that angles 2 and 4 are congruent because they're vertical angles. Angle 4 is congruent to angle 2 by the vertical angle congruence theorem. And then how do I show that angles 3 and 4 are congruent? Well, if angle 3 is congruent to angle 2 and angle 2 is congruent to angle 4, we can either do a substitution or we can use the transitive property. It actually works both ways. I'm going to say that angle 4 is congruent to angle 3 by substitution. If we take this 3 out and we put in the 4, we've got to take this 2 out and put in the 3, then we have this statement. Okay, and then if angle 4 and angle 3 are congruent, then lines E and G, E and H, that is, are parallel, because this and this are a pair of alternate exterior angles. And the theorem that says that if those two are congruent, then the lines are parallel is called the alternate exterior angles converse. So, again, you could pause the video here to make sure everybody's written down that proof before you move on. All right, and then the final proof from this page says that WF bisects angle AFJ. AFJ. Okay, so angle 1 would have to be congruent to angle 2 because of the definition of an angle bisector. When an angle is bisected, it carves that angle into two equal pieces, so those two parts would have to be congruent. That's what the definition says, so that's why we can go from here to here logically. Okay. On the next page we have some vocabulary. The first one has to do with interior angles. Basically, interior angles are angles that are on the inside of a triangle or whatever shape you're talking about. So this one here is an interior angle, this one's an interior angle, and so is that one. Exterior angles are actually on the outsides of the triangle. So angles that form linear pairs with the interior angles are exterior angles. So this is an exterior angle because if you put that together with the inside angle, it would make 180 degrees. That's called linear pair. Or this one's an exterior angle because if you put those two together right here, that would make half a circle as well. So anything where if you extended this out to make half a circle this way or half a circle that way, those would be called exterior angles. So over here you would have this one or this one, and then finally this or this. Those are called exterior angles. Notice that exterior angles are not in the center here. They are kind of on the sides. If you extend this out into a crisscross, they're going to be on the sides. A corollary to a theorem is basically a statement that can be proved easily by a theorem. It's kind of like something closely associated to a specific theorem. It's not super important that you know what that is. It's very similar to a theorem, basically. Again, interior angles, exterior angles. Okay, now classifying triangles is pretty easy and straightforward. If you have no sides that are the same, you can see this side is the longest and that one's the second longest and that one would be the shortest. If you have no congruent sides, that means that you have a triangle called a scalene triangle. None of the sides match. If you have a triangle where at least two sides are congruent, that triangle is called isosceles. Usually we say that it's exactly two sides that are congruent, not at least, but basically two sides congruent, you can call it an isosceles triangle. An equilateral, equa means equal, lateral means side. That means all of the sides are equal. So all three of them measure the same. Then you can call it equilateral. So let's see. This one would be having two sides that are the same. So this one is called an isosceles. This one has all three sides the same, therefore that would be equilateral. And this one, none of the sides match, so that is called scalene. Now you can also classify triangles based on their angles. So, for example, if you have a triangle where all three angles are smaller than 90 degrees, that's called an acute triangle. A triangle where you have one right angle is called a right triangle. A triangle where you have one angle that's bigger than 90 degrees, for example right here, that is called an obtuse angle, or obtuse triangle. And finally, a triangle where all three angles are the same as each other, that is called an equiangular triangle. Angular means angle, equa means equal. So all angles being equal, three congruent angles inside. So how do we classify these examples down here? Well, see, this one has one angle that's larger than 90 degrees. That would be an obtuse triangle. This one has a 90-degree corner, so that one would be called a right triangle. And this one has two angles that are 75, and then one angle that's even smaller than that. This would be called an acute triangle.